is commutative, that means you can switch up the order and you'll get the same thing. So that means A and then funny looking symbol B should be equal to B funny looking symbol A. Okay, so you can imagine this being the row and this being the column. So A in the row and then B in the column. If you match up where those two things link up, they link up right here for B. So that's the output. So B and A, that means B in the row, A in the column. It's going to give us B. So right now it's looking commutative. To be sure that it's commutative, we'd have to check all the possibilities, which there's a lot. Let's just pick another one. I mean, this isn't a super mathematical way of doing it, but if you pick like 3 or 4 of them and you're good to go, then if they're all working, then for at least Newton's sake, we're pretty sure that it's going to be commutative. So C paired with D. Let's see if that's the same as D paired with C. So C paired with D gives us A. And then D paired with C gives us A. It's looking commutative. Myself on something that I hadn't seen in a while. If this square here is symmetrical about the diagonal, then it's commutative. So that's not a real mathy way of being sure that it's commutative, because that's not really using the definition of commutative, but it sounds like that's a quick trick to find out whether it's commutative. If you get the same thing, like if you split it on the diagonal and you get the same thing on the bottom left as you do in the top right, then it's commutative. And it looks like it, right? There's A's, D's, and B's that are directly across from each other. These C's, these E's, and these D's are directly across from each other, so it looks commutative. So because we have an option, it's either a group or commutative or both. For it to be a group, it needs to be closed, which means every element in the rows has a chance of pairing up with every element in the columns, and it does, right? A connects with B, A has a chance of connecting with C, and A has a chance of connecting with D. So if you have A, B, C, D in the row, you've got to have A, B, C, D somewhere on the columns. So we're good. It's closed. For it to be a group, it needs to have an identity element, which means it's one element that always spits out whatever you pair it with. So let's see. It looks like it might be A, because no matter what you do with A, no matter what you pair it up with, it always spits it back out. A paired with B gives you B. A paired with C gives you C. A paired with D gives you D. So A is the identity element. So there is an identity element. Let's see, what am I forgetting? It's closed. It has an identity element. It's commutative. Invertible, the identity element needs to be in every row and in every column. And that's not the case. We have A, the identity element, in this first row. We don't have A in this row. So it's not invertible. Okay, that's a quick trick, and we talked about the inverse in another video like these two. But a quick trick for finding whether these are invertible is that identity element that we pick out earlier needs to be in every row and in every column, and that's not the case here. So that means it's not a group because it's not invertible. There's an identity, but not every element has an inverse. Question, because currently as of this video, Newton has this programmed incorrectly. It has the wrong answer programmed. Newton says that D is the identity element, but it's clearly not, right? Because if you pair A with D, it gives you D. If you pair if you pair B with D, it gives you E. That's not an identity element at all. So Newton has something incorrectly programmed. Newton's incorrect answer right now is it is a commutative group. Okay, but hopefully they'll have it fixed by the time you run into this question.